Okay, what we're looking at it tonight is a B&K 1477. It's a 15 megahertz scope. Oh, round about 35 years old. And it's been scrubbed, cleaned, switches have been cleaned up, the pots have been lubricated, calibration's been given to it, the cabinet's been cleaned up inside and out. Gave the cabinet a new paint job. Cabinet looks brand new. I did a very good job on the paint. I don't have all the screws back in the cabinet yet because I was maybe going to have to touch up on the cowls. We'll see how that goes as we give it a test here. But I've got new knobs on the front here. New old knobs, let's put it that way. The original knobs that were on here were damaged. Somebody had used some kind of a very harsh cleaner on the plastic, and the plastic bubbled. So all of the knobs had that on it. I removed all of the knobs and replaced them with these. These are from another B&K scope that I couldn't get working, so it's a good use for it. And as you can, if you look closely here, you can see that this lens frame shows some of the bubbling on the plastic. I don't have another lens frame, so I couldn't replace that piece. But with that exception, this is a fine looking unit, and I think you'll be able to look past that, especially if we get the price right here. We're going to take the thing through its calibrations, its checks, and I think you're going to find that it's working great. Right now, what we're displaying on it, just for fun, I have a sweep generator, this IEC 20 megahertz sweep generator. It's an F77, very nice unit, high-tech, and this sweep generator is sweeping from right now about 100 hertz up to about 100,000 hertz before it resets. It's doing it in a logarithmic fashion, so slow in the beginning and very fast at the end. And it's fun to see it's kind of sprung. You can almost imagine in your head what's happening here. Boing, boing, that kind of noise. That's for fun. What we have our working intensity control. We can take the intensity from something you can't see to something that very definitely has more than you need. We'll bring it back down to a reality here. Let's say something about like that. Focus works great. The illumination of the grid is great on this. You've seen the grid come into view there. Okay. All of our switches work very nicely. Let's see if we can kill the sweep for a moment and just look for jitter. Little hop, not too bad. As you play with the knobs, especially the position knobs, you kind of introduce a little bit of this jump, and that can be worked back out using the position knobs, and there's a center connector there for the balance. But you don't see any big jumps where you're flying up 3-4 divisions up the screen. That's because she's been cleaned and cowled. All of our hops here are remaining within about 0.2 divisions. Alright, and how about the variable knob? Okay, triggering. Let's give ourselves a signal so we can see what we're dealing with. There we go. Ground. Triggering. This is in auto mode. That's out of sync. In. And then the other extreme out of sync. And if you go to normal, we're triggering on, we're centered right now and we're getting a trigger pulse. But if I go out of sync, you get nothing. And that's the way it should be. And nothing again. I usually like to run in auto. I just prefer it that way. We have a ×5 position magnifier. That did not work when I got it, but it does work now, as you can see. And then we can move the trace left and right with its position. Okay. And you can change the source of the triggering from channel A to channel B. Either one works. Positions. All right. We have channel A, channel B only, both together, A plus B, A minus B. A and B are the same, so A minus B is nothing. Okay, so far so good. We're working great. Let's run this thing through its calibration checks and see how we fare. We're going to go ahead and give you a look at the interior of this scope. I opened it up to give it a little tweak on the calibration, but I wanted you to be able to see that the scope is in good shape. It's clean on the interior here. I'm going to close it up and we're going to go ahead and continue with calibration checks. We are right now set up feeding a 10 Hz signal in from our synthesized frequency generator. And that 10 cycle per second or 10 Hz waveform being shown right now on the 0.1 second per division. 10 Hertz, well, let's start with a kilohertz. We all know a kilohertz has a time period for one cycle that's equal to 1 millisecond. So if I was to bring in something that has a longer wavelength, so if we go from 1,000 cycles per second then to 100 cycles per second, that'd be 0.1 kilohertz. I'm going to have 10 times the wavelength. So we had 1 millisecond, that puts us at 10 milliseconds. So 100 hertz would have a cycle in 10 milliseconds. A 10 hertz signal, so we have a 10 hertz signal running at 0.1 seconds per division, and we get exactly one cycle in a division, because one cycle of 10 hertz takes 1/10 of a second to complete. So if we go to 50 milliseconds per division, now we're sweeping faster across the screen with our trace, and we're not giving the waveform as much time to display. In fact, we've cut the display time in half. So we're only going to get half of the waveforms that we did earlier, or half the cycles across the screen we did earlier. So instead of having 10 cycles across the screen, we now have 5. Okay, and then I'll still be able to see the controls. So now, if we were to go to 20 milliseconds per division, we've now cut the time by 1/5 of where we started. So instead of 0.1 seconds per division, we now have 0.02. Because 0.02 times 5 is 0.1. A little quick math. And we're now running 20 milliseconds per division, then across the screen we have 200 milliseconds. So if it takes 100 milliseconds to display one cycle of the signal, then in 200 milliseconds we're going to get 2. So there's 2 cycles on that screen right now because we're running at 20 milliseconds per division. And we have 10 divisions across the screen, and we got a 10 hertz signal on the screen. Now if I go to 10 milliseconds per division, 10 milliseconds times 10 divisions is 100 milliseconds, which is the time needed for a 10 hertz signal to display one cycle across the screen. And we see one cycle right now perfectly displayed across the screen because the time base is accurate on this unit. Okay, now we're going to kick the frequency up. We're going to go to 100 hertz. Alright, there's a 100 hertz signal. And if we look carefully, we should be able to see that there is one cycle completed in every division across that screen. But if it's a little hard to see, we'll make it easier as we speed up our trace. We're now running 5 milliseconds per division. So we're running twice as fast as we were. That means we can only get half of the number of cycles displayed on the screen that we did. So instead of having 10 cycles, we have 5. And at 100 hertz, we should have 10 milliseconds needed for each wave. And if we have 5 milliseconds per division and there's 10 divisions, that's 50 milliseconds across the screen. So our necessary 10 milliseconds that we need for that 100 hertz signal divides into 50 milliseconds 5 times, and that's why you get 5 cycles on the screen. Alright, we're running 2 milliseconds per division now. That means we have 20 milliseconds across the screen. It takes 10 milliseconds for a 100 hertz signal to have a cycle, so therefore we get 2 cycles on the screen. I can set the screen up so it's easier to see, right about like that. Now we've one cycle that way and one cycle the other way, and both ends hit on the end. So we've got exactly 2 cycles on the screen. And then we go to, 1 millisecond per division. And we are able to display in 10 divisions 1 full cycle of that 100 hertz signal. And it's perfectly displayed here. Alright, we're going to kick our frequency up again. We're going to go to 1000 hertz now. Okay, now at 1000 hertz, running 1 millisecond per division, we should have 1 full cycle in every division. And we do. I'd be disappointed if we didn't. There's exactly 1 cycle in every division there. If I go to 0.5 milliseconds per division, we get 5 peaks because we have half the time. If we go to 0.2 milliseconds per division, we get 2 cycles displayed on the screen because we have 1/5 the time that we needed to have the 10 cycles originally displayed across the screen. Again, this is at 1 kilohertz. And 1 kilohertz in 10 divisions. See, right now we are at 0.1 milliseconds per division. In 10 divisions, that's 1 millisecond. If I'm displaying 1 millisecond of time across the screen, I'm going to get one cycle of a 1000 hertz signal across the screen. And that's exactly what we have. Alright, let's go to 50 microseconds. And let's kick our frequency up again. So, I kicked my frequency up to 10 kilohertz. And at 0.1 milliseconds per division, I'm getting one cycle per division, which is what you'd expect. Now if I go to the 50, I get 5 cycles. 20, I get 2 cycles. 10 microseconds per division, I'm able to display my 10 kilohertz signal. I've got one cycle of that 10 kilohertz signal displayed across the 10 divisions of the screen. And again, it's perfect. It was calibrated that way, so that's what we want. And back down. We're going to raise our frequency up again. Alright, we are running 100 kilohertz. And we are running 10 microseconds per division. We're getting one cycle per division, which is what we should get. If I go to 5 microseconds, we get 5 cycles. 2 microseconds per division, we get 2 full cycles. 1 microsecond per division, and we get 1 full cycle of a 100 kilohertz signal displayed across the screen. And it's showing perfectly. Raise our frequency up to a megahertz. There we go. We are at 1 megahertz, and we are at the 1 microsecond per division, so we get 1 cycle in a division. Adjust my horizontal so we can get it right on the line there. There we go. So we start our peak here. There's come up, come down, come up. 1 full cycle in a division. That's exactly what we want. If we go to 0.5 microseconds per division, we get the familiar 5 peaks, which is what you'd expect. And then the final position is our XY position. Since we're feeding the same signal in on both channels, we're getting the common Lissajous pattern that would indicate that the signals are equal. We have a single lobe shown on the screen. Go back to the 0.5 microsecond per division. If I was to multiply that times 5, then I should be back to showing 1 trace across the screen. And we pretty much are there. That's so we just had an extraordinary look at the accuracy of the scope, its calibration. We were perfect through all of the ranges. Every range step showed us exactly what we wanted to see in the right time. And just for fun, we had it shown on both channels simultaneously, although since they share the same time base, you really only needed to prove it on one. But the time base is proven out. We have accuracy on our time base. The calibration was a success. We'll move on.